Okay, force of gravity. I kind of just realized I did some examples previous videos where I applied like a force of gravity to like a free body diagram to find equations of motion, and I never actually talked about what gravity is. So I'm gonna do that now. Better late than never. So every object in the universe exerts some gravitational force on every other object in the universe, which is wild to think about. For me, everything, everywhere, is interacting with each other on some scale, right? So you are gravitationally attracted to your ex. If you're groveling 10 feet away from your ex, you might not have the same flair that you once had, but you are gravitationally attracted to each other. The Golden Gate Bridge in California and San Francisco is gravitationally attracted to the Statue of Liberty over in New York. That's about 3,000 miles away. A penny on Earth would be gravitationally attracted to a penny in the Andromeda Galaxy, which is the nearest galaxy to the Milky Way. And that's 2.5 million light years away, or 14.7 times 10 to the 18 miles, which is 14.7 quintillion miles away. Those two pennies are attracted to each other on some scale. It's practically zero, but it's not zero, right? So just kind of wrap your head around that. That's wild. So let's talk about what this force is. So say we have two bodies in space. We have M1 and we have M2. And we have our reference frame set up here such that EX points from M1 to M2. EX is the unit vector that points from M1 to M2. R is the vector that points from the center of mass of M1 to the center of mass of M2. And the way I have it drawn here, it could be a little misleading. I just didn't want a bunch of overlapping lines. It really should be like this. Okay, it should be pointing from the center of mass of M1 to the center of mass of M2, but just pretend I don't want a bunch of overlapping lines. F12 is the force that body 2 exerts on body 1, and F21 is the force that body 1 exerts on body 2. Right? So for 1, 2, the mass 2 is pulling M1 this way. And then for F21, M1 is pulling M2 this way. And I already talked about what R is. Okay, so let's move on. Where the magnitude of F12 is equal to the magnitude of F21. And the only difference is that they act in opposite directions, right? The force that one body exerts gravitationally on another body is the same that other body exerts on the other one, right? They're equal and opposite. So F12, it points in this direction, it points in the positive EX direction. And then F21, it's the same magnitude, it just points in the opposite direction, right? So they're mutually attracting each other with the same force. So that's what this is saying. It's saying F12 is equal to negative F21, right? And that makes sense, right? F12 is pointing this way, F21 is pointing in the opposite direction, same magnitude. So just negative F21. And you could also write it like this, F12 in the EX direction and negative F21 in the, or F21 in the negative EX direction is how I think I'd say it. Okay, and EX, you could write this unit vector EX is the vector R divided by the magnitude of vector R. And when you take the magnitude of a vector, you drop the underbar, right? So this is just the magnitude of R. And this will give you the unit vector, right? And we've talked about this before. If you have a vector and it's pointing in a certain direction, if you divide it by its magnitude, then you get the unit vector, right? And R points from the center of M1 to the center of M2, which is the same direction EX points in, right? So just another way to write it. And okay, so I kind of conceptually understand where all the forces are pointing and what gravity sort of means. But what is F12 actually equal to? Like, what is that force? Okay, well, Newton answered that for us. So behold Newton's law of gravitation. Voila, it's right here. This is it. So F12, so this is the force that body 2 exerts on body 1. That's this one. That would be equal to G. I'll talk about what G is in a second. M1, M2. So this is the mass of our first body and the mass of our second body, divided by the square of the distance between them in the EX direction. That is F12. We could also rewrite EX as what we, called it up here, like this. And you can see that, we have another R here, and it can get absorbed into this R squared and become an R cubed, right? So all of these are just variations of writing the exact same thing. But this is Newton's Law of Gravitation. So what is this big G? This big G is what's called the universal gravitational constant. And it's a constant, it is a number, and it just happens to have the value 6.674 times 10 to the negative 11 meters cubed per kilogram second squared. This is just one of those numbers that is it just happens to be a constant in our reality, in in physics, in our universe. The way our laws of physics work in our universe is one of those knobs that it just is what it is. This is the number. All right, that's what G is. So let's look at Earth. Okay, so let me talk through this picture real quick, and then we'll dive a little deeper into it. So this is the same thing we had up above, this M1, M2 body diagram, right? So M1 in this case, M1 is the Earth. That's what that sphere is. That is the Earth. Here's the center of the Earth, that red dot. We have this body, M2. It doesn't matter what it is. And it's a altitude of h above the surface of the Earth. So it's h above the surface of the Earth. And we still have our vector r, which points from the center of mass of the Earth, in this case, to the center of mass of M2. That is still r. Ex is the unit vector that points in the direction of r. And we have F21, which is the force that body 1 exerts on body 2, right? So it'll be going in that direction, all right? And the Earth has radius r, and it has a radius approximately 4,000 miles. Or at least that's what Google told me when I put that in. Okay, so F21 is equal to negative F12, right? We already talked about that right here, right? I'm just plugging in. Negative F12, which is equal to negative, and this is our Newton's Law of Gravitation, G M1 M2 over R squared in the EX direction. So the denominator here, r, this is equal to the magnitude of vector r, which we wrote like this, and that is equal to, well, how do we get from the center of mass of the Earth to the center of mass of our body M2? Well, we travel from the center of the Earth to the surface of the Earth, and that's a distance of r. And then from the surface of the Earth, we then have to travel a distance of h. How high above the Earth are we? H, right? So r plus h is the magnitude of r. R plus h, big R plus h. That is the distance from the center of the Earth to body, to the center of mass of body 2. And so we can plug this in. We're just plugging this in for the denominator here, which is what we get right there. And if we take r out of these parentheses, right, we take r out, well, then this now becomes 1 plus h over r, and this whole quantity squared. And then we can distribute the square. So we have r squared times 1 plus h over r squared. I just took the r out. That's all I did. And as long as h, so how high above the surface of the Earth we are, as long as that is a lot smaller than r, the radius of the Earth, then this term, h over r, is going to be practically zero, right? If in the denominator you have a really big number, and in the numerator you have a really small number, it's going to be basically zero, right? So that kills this term, right? So all we're left with in the denominator is just this right here, r squared. R squared. So the force of the Earth on our body 2 is approximately this. Is it exactly? No. Is it close enough? Yeah. Yeah, it is. And so the magnitude of this force, F21, is approximately just g m1 m2 over r squared, right? There's only one component, ex, an ex component, and the negative becomes positive when you take the magnitude, so it's just g m1 m2 over r squared. That is our magnitude of force F21. Now, let's just look at this right here, g m1 over r squared. G m1 over r squared. So that's this. And let's plug in the numbers. Let's plug in some numbers. So this is g. This is the universal gravitational constant. It's just a number. The mass of the Earth, according to Google, is 5.972 times 10 to the 24th kilograms. And then over 1 over r squared, well, r is 6.371 times 10 to the 6th meters. That is the radius of the Earth in meters. And we square that. When you plug that into your calculator, you get 9.81 meters per second squared. Does that look familiar? Because it should, right? In high school physics, in physics 1 and 2 in college and stuff, this comes up all the time when you're calculating like the force due to gravity. And that's because that is the magnitude of the acceleration due to gravity on Earth. On Earth, right? If we went on to the moon or something, right? The mass of the moon is much smaller than the mass of Earth, and the radius is also smaller, right? So the local acceleration on the moon is going to be smaller, right? That's why you weigh less on the moon than you weigh on Earth. Okay, and this is the local acceleration is a vector, which we call g. Notice the underbar, it's a vector. And that is equal to negative g m1 over r squared ex, right? So this is just rewritten from above, right? The force was approximately negative g m1 m2 over r squared ex. And we're going to call all of this, basically everything except the m2, that is now called g. That is now called g. So the force of the Earth on our some body close by above the surface of the Earth is just m2g. The mass of our body times g. So the force of gravity, which is what I've used in the previous videos and what we're going to be using moving forward and everything, is m times g. Okay, that's it. We're going to have plenty of examples applying this, but this is where, the mg comes from, and why when we apply the force of gravity on our free body diagram, this is what we'll be using. Okay, all right, I'll see you in the next one.